Alright, so in this video, I am going to derive this equation here and kind of talk about what it means. But first, let's just recall the definition of current. Current is a quotient. It is the amount of charge passing through some cross-section of conductor per unit time, right? And so I can write this in an expression as I is equal to dq dt, right? If some difference in charge divided by some difference in time. Or, I can also write that as delta q over delta t, some change in charge over some change in time, kind of the same thing here. But from the previous slide, I also know that the current through a capacitor is equal to C times dVc dt, right? If I'm looking at a capacitor, I'm talking about the current through the capacitor being IC, and I'm talking about the voltage across the capacitor being Vc, okay? And so what I'm saying here is what I'm saying here is that this is the general definition of current. It's the change in charge over the change in time. But specifically for a capacitor, I'm saying that this is the IV relationship. So considering that this is a current, I can use this equation here and I can equate them because they're both currents. So I can say that dq dt is equal to C times dVc dt. Or, equivalently, I can say delta q over delta t is equal to C times delta Vc over delta t, okay? And you can see pretty easily that the delta t's cancel. And so what I'm left with is just delta q equals C times delta Vc. And so maybe I'm interested in some q final minus q initial. Maybe that's my delta q. And I say that that's equal to C times some final voltage minus some initial voltage. Well, in most of the cases, what we're going to be dealing with is we're going to be dealing with a capacitor that started with no charge and no voltage across it, and then sometime later it's charged. And so if that was the case, then my initial voltage would be 0, and my initial charge would also be 0. And well, what I would be left with is Q final, or just Q, I could say, is equal to the capacitance multiplied by the final voltage. And so that's basically the expression that I have here, right? These are equivalent expressions. And so what this expression means is it basically means if I know how much charge my capacitor is storing, if I know the capacitance of my capacitor and the voltage across it, then I can determine how much charge it's storing. And equivalently, if I were to rearrange this, I could write V is equal to Q over C. And so if I know the amount of charge being stored in my capacitor and I know the capacitance, then I could determine the voltage across it. Okay, so that's what this equation is useful for. CV equals Q is something that you're going to hear a lot, you're going to use a lot. It's very important to remember, and I just wanted to take the courtesy to derive it really quickly so that we understand where it comes from. It really just comes from equating the general equation for current, which is the rate of change of charge over time, with the current specifically for a capacitor. And then you set those equal to each other, time cancels, and you can start with some initial charge being 0 and initial voltage being 0, and sometime later when you charge your capacitor, it'll have some final voltage and some final amount of charge. Capacitance is constant. Okay, so just wanted to go ahead and go over that concept. In the next video, I'm probably going to talk about, actually, you know what? Let me just real quickly give an example. So if I had a capacitor that has 5 volts across it, and I know that this is a 1 microfarad capacitor, I could very easily determine how much charge is stored on this capacitor by using my equation here. I could say Q is equal to C times V, which would be 1 microfarad times 5 volts. And so then I would know that the amount of charge stored on this capacitor would be 5 microcoulombs. Okay, so coulombs is the unit for charge. And so just so that I don't have to do that in a separate video, I wanted to throw that little example in here. In the next video, I'm going to talk about how we combine capacitors in series and how we combine them in parallel. We learned that for resistors. Now we're going to learn it for capacitors. Okay, so I'm going to end this video right here.